Hello AP Physics 1 students. Please make sure you've printed out your capacitor and circuits concepts pages, and I want you to, on your own, do numbers 1 through 9, pause the video as you do so, then come back and we'll discuss some answers. Just numbers 1 through 9. Okay, so we're just going to be going through a lot of concepts here, starting with number 1, which moves voltage or charges, and so hopefully, of course, you said is the charges that move. If we go back to our ski resort analogy, the charges represent the skiers, right? The skiers move, so the charges move. And plus voltage, remember, that's like a difference in height. That's like the mountain itself. If you go back to our analogy, the mountain doesn't move. And so really just want to make sure we're using our vocabulary correctly. And unfortunately, sometimes even professionals talk about the voltage moving through a circuit, the voltage moving through a resistor or something like that. That's completely wrong. The voltage doesn't go anywhere. The voltage is there, the potential difference is there, but the charges are the things that move. And of course, when charges move, that's called current. Alright, number 2, what's gained and lost? And of course, that's voltage. Here again is just a matter of making sure we understand our vocabulary. What does current measure? Well, as we just said, current measures the rate of flow of charge, right? You can't gain or lose charges. That's like gaining or losing skiers on the mountain. It doesn't make sense, right? By conservation of charge, you can't lose these actual objects. But voltage, what does that measure? That measures energy per charge, and the charges certainly do gain and lose energy. Voltage gained through the battery, voltage dropped through the resistor, and so it is the voltage that is gained and lost. Number 2, do charges pass through a capacitor? Of course not. Remember, we talked about over and over how the capacitor plates are a gap. There's either air in between them or some sort of insulating material, and, well, it can be convenient as we look at a circuit combination of capacitors in a circuit to think about charges flowing around because it helps us visualize whether it's series or parallel. It's completely wrong. You have to remember that once the capacitors charge up, the charges stop moving when all conducting surfaces are equipotentials, and that's it. They don't move, right? And so if you put a capacitor in a circuit even with resistors, in our case here in this course, we're only going to deal with the case where the capacitor is uncharged or the capacitor is fully charged. And once the capacitor is fully charged, it has the charge across, has the charge on it, has the voltage across it, and then that's it. It's like a gap in the circuit. There will be no more current going to either plate of the capacitor. Number 2, which charges do we consider? Well, of course, we do our conventional current. That's going to be protons. Even though we know in our heart of hearts it's really electrons, it doesn't matter. Because remember, if we're all wrong together, we must be right. Out of which battery terminal do charges flow? Well, of course, that's going to be the positive, represented by the long line. Sometimes the long line on the circuit diagram will show positive, sometimes it won't. But you have to remember, as you're tracing charges around, it's always a good idea, I think, to start at the positive terminal of the battery and just sort of watch the charges that go up and down the mountain, gain through the battery, drop through the resistors. It helps you visualize what's happening. All right, number 6, this happens all the time. You know, of course, with our simulation, you had to sort of make it happen, but in real life, there's always some unwanted voltage drops. That happens in the wires. We think about the resistance of a wire, rho L over A. Anytime there's a resistance, delta V equals IR says there will be a potential difference, and that means there's a voltage drop. And remember, in a real battery with an internal resistance, there's going to be a voltage drop there as well. A lot of times in the problems, they say, you know, a source of EMF with negligible internal resistance. They're telling you that little r equals 0. They'll say that they're ideal wires or wires offer no resistance, so we pretend that they're conductors with no resistance, but in the real world, this always happens. Okay, so here's, you know, by putting all the circuits together, we should have been really good at this. Ammeters are connected in series. Since ammeters measure current, you want all the charges that will either eventually go through the resistor or has already gone through the resistor to go through the ammeter. So it's got to count all them up. It's got to be in series, one after the other. But of course, the voltmeter should be in parallel. You want a junction there. Either the charges go through the resistor or they go through the voltmeter. We don't want the voltmeter to change the circuit, alter it in any way. So it should provide an alternate path there to make sure it doesn't change anything about the circuit. All right, number 9 should have been really simple because once you recognize that resistors in parallel are very much like capacitors in series, either you can just jump right to the equation or do some very easy algebra to get this equation. It's R1, R2 over R1 plus R2, or the product over the sum. Again, if you'd like to box this in as maybe a semi-quasi-new equation in a dashed line, you certainly can add to your list as long as you recognize it's only for 2 resistors and it's only in parallel. And it's only for 2. It doesn't keep going. You can prove to yourself with the algebra that once you do 1 over R1 plus 1 over R2 plus 1 over R3 and start doing the algebraic manipulation, it gets much more complicated. You cannot just keep putting R3, R4, R5 on the top and plus R3, plus R4, plus R5 on the bottom. That does not work. is only for 2 resistors in parallel, and the similar one is for 2 capacitors in series. Now, if you do have more than 2 of these devices, you can sort of pair them off 2 at a time and do this easy shortcut, and then just keep reducing and reducing and reducing the circuit to make it simpler. Or you can just do it all at once using the usual 1/x button on your calculator. Okay, now let's get to problem number 10. I want you to just read it real quickly. It's basically just telling you to solve everything. Solve for total resistance, total current, voltage drops, currents in each of the resistors. And the goal here is actually to do it as quickly as possible. Imagine this were a multiple choice question on the AP exam or on our test, and you want to not even touch your calculator, want to try to do as much of it in your head as possible. So what I'm going to do is I'm going to pretend I'm drawing the circuit. This is what I would do in class. I would draw the circuit on the board, and by the time I finish drawing the circuit, you should actually be completely done with solving problem 10. So don't pause the video here. I'm going to show you, time out how much I would be doing it, and I want you to solve it as much as you can. Ready, and go. Okay. So drawing the battery. Here I'm drawing wire. I'm drawing R1. I'm drawing R2. I'm drawing more wires. And I'm completing the circuit. Now I'm labeling the 12 volts, 6 ohms, 3 ohms, and done. And in that short amount of time, you should actually have been done. Now, don't do any more, because I want you to see just how quickly this could be done. More than likely, first thing you did was find REQ, but you really don't have to do that, because first thing we do is we notice that these resistors are in parallel. We say to ourselves, what do we know in parallel? Well, the voltage drops are going to be the same. This has to drop 12 volts, this has to drop 12 volts, no matter what, right? Any charge gaining 12 volts has to drop 12 here, has to drop 12 here if we're going back to the battery. What can we solve for this? Well, look, I even wrote voltage over resistance, so we know the current's going to be 2 amps here, the current's going to be 4 amps there. 12 over 6, 12 over 3. And now if we see 2 amps here, 4 amps here, that means the total current had better be 6 amps, which I draw here, right here on the circuit diagram coming out of the battery. And then what's REQ? Well, if this is 12 volts for 6 amps, that's got to be 2 ohms, and we are done. And that's how quickly it can be done. You don't necessarily have to find REQ first and I total. Just do what you can. And look what I did. I did it right here on the circuit diagram. This is a multiple choice question. You're not going to show all your work and write down the equations and all that. Just do it, right? And the more you can write on your circuit diagram, the more visual it is. Okay? So now for number 11, do the same thing. Just, this time I will ask you to pause the video, but solve problem 11 as quickly as you can, writing down as little as you can, touching your calculator as little as you can. Go. And we're back. So hopefully, first of all, you should have noticed that all 3 of these are in parallel. And we know that parallel connections are independent of each other, which means putting R3 here actually shouldn't affect anything about R1 and R2, which means they do the exact same thing they did before. Since these are the exact same resistors connected to the same battery, there's literally nothing different but what the 6 ohm resistor and the 3 ohm resistor do in this circuit compared to this circuit, at least ideally. Of course, in the real world, there might be some minor differences with, resistance of the wires and things like that. But in this perfect physics world, they do the exact same thing, and so we don't want to reinvent the wheel. Just write down their values. Now, since the 9 ohm resistor is in parallel, we know it's got to drop 12 volts, and 12 volts for 9 ohms, that's 1.33 amps. Done. If we have 6 amps from before and 1.33 amps, we know the total current is going to be 7.33 amps, and 12 volts for 7.33. Okay, at this point, maybe you do have to break out your calculator. I know I do as well. We should be getting 1.64 ohms, which then you could verify if you'd like to by doing 1 over 6 plus 1 over 3 plus 1 over 9 and taking the inverse, and we should get 1.64 ohms. But once again, we try and do as much as possible. Now, of course, if this is on the test or if this is on the AP exam in an FRQ section, well, then you do have to show your work. So yes, you certainly can label everything on the circuit as much as possible, and I want you to, and do as much ahead as you can. If you want to earn credit, of course, you have to show some equations and show the numbers plugged in. Alright, so here's number 12. Again, try to do as much as you can on your own, in your head, and write down as little as possible. Come back to the video to see the solution. So again, we want to try to not reinvent the wheel. So we should see the 6 ohm resistor is doing exactly what it was before, so it's got to drop all 12 volts. And of course, it's going to have 2 amps going through it. Now the 3 and the 9 have been rearranged. What sort of connection do they have? Well, they're in series. Okay, so now we have to take a couple extra steps. We can't say the 6 is in parallel with a 3. That's not true. We also can't say the 6 is in parallel with a 9. That's not true either. The 6 is in parallel with this whole combination. So here it's a matter of choice what you want to do, but let's try to do it the same way we were doing before. We know there's a total of 12 ohms on this path. So imagine Or you can redraw if you'd like to, replacing these two with a single 12 ohm resistor. Now 12 volts has to be dropped by the combination of 12 ohms, and so 12 volts or 12 ohms, that's got to be 1 amp of current. And they're in series, so they're each going to have the same current. Now, at this point, maybe don't draw these currents. Listen to what I'm going to say here. Now it's a matter of choice. Here's what I like to do. I know this entire branch is going to have 1 amp of current. So personally, I draw 1 amp of current in the 3 ohm resistor and 1 amp of current in the 9 ohm resistor. However, I know from experience, some students look at this and get confused and think this means there's a total of 2 amps on this branch. Now, if that's you, if you looked at that and said, that's 2 amps, then don't do what I'm doing. Instead, draw just 1 amp of current down this entire branch and just draw it once. There's nothing wrong with this, that neither way is better than the other. It's really a matter of what's going to make sense to you. And so, if this makes more sense to you, and you can understand that each of these resistors has 1 amp, that's what you draw. Personally, this is what I draw. And again, sometimes I tell you do it my way because it's better. This is not one of those cases. I literally want you to do it whichever way works best for you. Now, I'm going to leave this up here on the PowerPoint because that's the way it works best for me. But if it's not working for you, don't do it. Okay, now what can we do? Well, there's all sorts of things we could do. We could say there's 2 amps here and there's 1 amp here for a total current of 3 amps, which again we draw by the battery. I always want to draw I total coming out of the battery. I think that's the easiest way. Certainly you could also draw it going here as well if you like to, because 3 amps splits to 2 and 1 and it comes back together as 3 amps. That makes sense to you, that's fine. And then we could say, well, each of these resistors has 1 amp going through it, so we know this has to drop 3 volts, this has to drop 9 volts, delta V equals IR, and this makes sense because we did say there's going to be a total of 12 volts dropped through the whole combination. And now we could do REQ, 12 volts, 3 amps equals 4 ohms. And of course, if you went in a slightly different order, that's fine too. As long as you solved everything and try to do as quickly as possible, not reinventing the wheel, that's the idea. Alright, let's go on to problem 13. Once again, try to do as much as you can on your own. This is getting a little more complicated, so maybe pause the video, try some stuff, and then come back to see the solution a little more quickly. Okay, so here it gets a little more complicated. Is the 4 ohm in series with a 6? Well, we can't say that, right? Because our real strict definition of series is if it goes through one, it must go through the next. And if it goes through the 4, it doesn't actually have to go through the 6 because it has the junction. It can either go through the 6 or the 3. So we can't say the 4 is in series with the 6. So if you combine 4 and 6 to make 10, that's wrong. We can't say the 4 is in series with the 3 either because of the junction. So if you combine the 4 and the 3 to make 7, that's wrong also. So at this point, maybe pause the video and try some other stuff and then come back to see what I do. So this is a case where really we should go in our traditional order of finding REQ first. And you look for the simplest combination. The simplest combination is the 6 and the 3. They're definitely in parallel with each other. So we're going to take these two out and replace it with a single 2 ohm resistor. How do I know it's 2 ohm? Well, this is exactly the same as problem 10. Right? We already know it, and certainly you could do it if you'd like to do the product of the sum, do a little shortcut, but it's going to be 2 ohms of resistance. And either draw it separately or just imagine it's 2 ohms of resistance, and then we say, if we take these two out, now this combination is in series with the 4 ohms for an REQ of 6 ohms. 4 ohms here, and a total of 2 ohms here. Now what can we do? Well, we've got 12 volts for 6 ohms. Well, now we can do total current. That's going to be 2 amps, which again I draw here coming out of the battery or going into the battery. Either one is fine, or both is fine as well. What should we do next? Well, you want to do something that you absolutely know. If you follow the charges coming out of here, 2 amps goes through the 4 ohms. All the 2 amps has to go to 4 ohms before it gets to the junction. So we know 2 amps for 4 ohms. We know its voltage drop has to be 8 volts. It has to. What do you do next? Well, a charge that gains 12 volts to the battery loses 8 volts to the resistor, and then we get to a junction. Some charges will go this way, some charges will go this way, but no matter what, if it gains 12 here, loses 8 volts, what is left for either of these resistors? Well, it's got to be 4 volts, right? Track a charge. Gain 12, lose 8. It has to lose 4 volts to get back to the battery. Gain 12, lose 8. This charge has to lose 4 volts by going through the 3 ohm resistor before going back to the battery. So either one is going to be 4 volts of potential difference, which of course makes sense because they're in parallel. Now what do we do? Well, 4 volts for 6 ohms, that's going to be 0.667 amps. 4 volts for 3 ohms, that's going to be 1.33 amps. And then what's our check? Well, 2 amps gets here and splits to 0.667 and 1.33. It comes back together as 2 amps. Or if 200 skiers go to the top mountain, that doesn't work. 2,000 skiers go to the top mountain, 667 skiers go this way, 1,330 skiers go this way for a total of 2,000 skiers. I'm just trying to do it with whole numbers. The point is that the charges get here, they split, they come back together. That's our check to make sure everything's working. All right, We'll take a look at problem 14, pause the video, come back to it to see how I do it. Again, we're trying to make sure we don't